chemistry time.
Mr. Cry.
Today. We're talking about ionic bonding. Please go sit down. Thank you. Thank you. An ion. An ion is what?
An atom that gained or lost a charge.
Okay, so yeah, I like that definition. An atom that has gained or lost a charge. Remember that atoms, technically when we use the word atom, we're talking about an electrically neutral fundamental particle of a particular element. So we wouldn't really want to use the word atom, but I can't think of a better way to do it. So we'll say, let's just keep it simple. An atom which has a charge. Charges in nature can be either positive or negative. We call those ions that have a positive charge what?
Cat ion.
Cat ion. And atoms that have a negative charge.
Anion.
An anion. The way I remember these, you might remember this from last year, the way I remember these is that the nice happy little cat
is positive.
And the stinky bad onion is negative. And then there's always I always say the thing that I do like onions and actually I do not like cats. So for me, as with many mnemonic devices, I actually just remember the opposite. I remember that to me an onion is positive, and so that's a negative charge, and a cat is negative, that's a positive charge. It's a good cat though. I don't dislike cats. Especially like if it's a tiger, if this is a tiger and not just a house cat, then that's very positive. You get 2+, that's like calcium, 2+. Speaking of calcium 2+, why calcium 2+? Yeah, let's start with look at where it is on the periodic table. This is a great, we talked about last time how the periodic table is a fantastic tool that we can use to learn all kinds of things about an atom, more than just what's shown. So calcium, even though it has all this very interesting information, calcium 20, simple Ca, 40.078 is its average atomic mass, etc. There's lots of stuff that's interesting about this, but just its location on here is what we're going to use for this. What group is it in? 2. And therefore it has how many valence electrons? 2. So we would draw its valence electrons like this. This is its electron dot diagram, calcium. When it bonds, what's bonding? What's
Two
bonding?
things coming together.
2 things coming together. Like welding. Webster's dictionary defines a welding as fusing 2 pieces of metal with a hot torch. You get my reference? No, because no one. It's from The Office. Michael Scott gives a speech at someone's wedding, and he starts it by saying the classic speech trope of Webster's dictionary defined. But then it's very clear that he's read the wrong entry. He says welding is defined as combining 2 metals with a hot torch, which is the definition of welding. So anyway, bonding, like a wedding, is the combination or combining of 2 or more atoms. Do they have to be of different elements? Should we write atoms of different elements? No, they don't have to be. They can be the same. Calcium wouldn't be a good example of that, but we could have another example. So when calcium forms a bond, it's combining in some way with some other or the same calcium atom that doesn't work with calcium.
That was at Pam's and
Jim's?
Was it?
No,
I don't think so. I think that was someone. I think it was at.
it was.
That was at Bob Vance and Phyllis's wedding.
Yeah.
Phyllis Lappin. She became Phyllis.
Phyllis was
Lappin.
fat and skinny.
Taylor, you need to take that back because everyone heard that.
Sorry, Phyllis. I
Okay. Good. Anyway, so calcium will bond with another atom so that it can lose these 2 valence electrons. Remember, atoms are generally more happier, I was about to say, and I guess I did say, more happier due to the octet rule when they have how many?
8 valence electrons.
8 valence electrons is stable, generally. Are there exceptions? Certainly there are. The 2 most important ones are hydrogen and helium are stable with 2. There are also exceptions within here, and there are some exceptions over here too, where not that they're happier with 2, but that they can be more stable with some other number than they currently have, but that number may not necessarily be 8. So calcium, in order to become more stable, would like to get rid of these 2 electrons. It can't just get rid of them. Your mom,
Hey, you're
not just you, y'all's mom wants to get rid of you.
Probably.
She does. That's how it is. we've talked about how every single person in this class except for Shylin has an older sibling that was also in this class. And we don't need to go into detail about who did a better job in chemistry or who was probably the better student at home. But
Shut up, Gabe.
those people all left. They're all out of the house now, to my knowledge. And your mom at no point could just say, "See ya, good luck on your own." They had to make sure my point is, your mom had to make sure that they had a nice, safe place to go. College, work, an apartment, whatever. Calcium can't just say, "See you later, electrons." It can't just bye-bye, electrons. The electrons have to go somewhere. This is one of the key, actually this is a state standard. One of the key pieces that you need to understand about chemistry is that these electrons, in order to be, as it were, removed from the calcium, have to go somewhere else. What might take the electrons from calcium?
Sulfur?
Yeah, sulfur, for instance. But some anion. So calcium, when sulfur, which has how many valence electrons?
6.
1, 2, 3, 4, 5, 6. When sulfur, which has 6 valence electrons, how many does it want? How many would it be most stable with?
8.
8. And so how can it become more stable?
Go down 2.
No.
Those 2
Gain
Sulfur has 6, so it wants to gain 2 electrons. Yeah. This should be even clearer. It's sometimes kind of sketchy. People don't quite understand that the 2 valence electrons in the calcium have to go somewhere. But it's pretty clear that sulfur can't just manifest 2 electrons. It can't just create 2 electrons for itself. It has to get them from somewhere. So these are kind of a nice match, just like Phyllis and Bob Vance of Vance Refrigeration. That this calcium can give its 2 electrons that it would be more stable without, to this sulfur that desires, or we shouldn't use that word, but it will be more stable with 2 valence electrons. So now we end up with calcium 2+, like I had wrote over there, and sulfur 2-. What? But this one lost electrons. Why does it has a positive charge now?
Because electrons have a negative.
Electrons have a negative charge, exactly right. So if it loses electrons, it now has a positive charge. Sulfur has gained 2 electrons and so it has a negative charge. And now they're happy, right? We use that term quite often, but they're more stable. Both of them are more stable, so they can both go about their merry way. Yes or no?
Yes.
Can they go about their merry way? No.
No.
Just
No,
like
they're bonded together.
Bob Vance of Vance Refrigeration and Phyllis, they're bonded together. Why? What holds them together? The bond of holy matrimony? I guess in some allegorical sense, perhaps. But what physical thing holds them together?
The valence.
Calcium's 2 valence electrons.
No.
The bond?
What? Yeah, this is a bond.
They're
What holds them
ionic
together?
bond.
Yes, it is an ionic bond. What's holding? What force of the universe holds them together?
The
The electrostatic.
Yeah.
Static. Well, it'd be
Okay.
the electromagnet.
I'm going to say electromagnetic because that's an actual
Oh.
fundamental force. The electromagnetic force.
Isn't
Why?
ionic bonding?
What's true of positive and negative?
They
They're
Attract.
Opposite
Just like Bob
attract.
Vance and Phyllis Lappin. They attract. They are held together by a force of nature called the electromagnetic force.
Isn't
And this force is also called an ionic bond. That is how an ionic bond forms. Generally, what kind of elements lose electrons?
The left
Metals.
side is stair step.
Metals. The left side is metals. Generally, what kind of atoms lose or gain electrons?
Non-metals.
Non-metals. So usually we find anions that are these, and cations that are these. Here's a little subsection of your boy polyatomic ions. Define the word polyatomic for me in Greek.
Polyatomic. No one answered this but me.
Okay.
Ions made of more than common polyatomic PAI.
It started out good.
Hold up.
I know I have it.
Polyatomic.
Ions made up of
Of more
other
than one
ions. Of more than one.
Ions
Poly-
made up of more than one ion.
Yeah. Poly meaning many, atomic meaning as. Ions made up of more than one atom is what this should say. Many atoms. So we have, give me an example. Each person give me one polyatomic ion and its formula and charge. Taylor?
Cyanide.
BRO -1.
BRO -1, what is that?
Bromine. Bromine.
Girl, don't you
Bromide.
dare use mine.
Bromate?
Are you maybe missing a
Maybe put
number?
like a number or something.
BRO
3.
BRO3 is bromine. Good, okay.
C,
Okay, Lily?
acetate. C2,
Oh, sorry. I'm sorry.
H3, O2, -1.
Acetate. Gabe?
My favorite because it's the easiest peroxide, O2 with a -2 charge.
Kendall?
Ammonium, which is NH4 minus 1 or
Mm.
plus 1?
+1. Cyrus?
He's sick. Gone.
We'll wait. Cyrus says,
I'll wait.
sulfate.
Yeah, that-
SO4 -2.
Yeah, he does. He is always saying that too. He's like a Pokemon, just repeating sulfate over and over again. I kind of ran out of room here. I'll erase my erstwhile Ca2+. Okay. Who else we got left?
Wait,
It was
just like-
Victory.
Wait, another one?
Sure.
Why can't I go?
Whitley, I mean.
NO3 -1 is nitrate.
Nitrate.
Cyanide. CN minus 1.
What's true of all of these?
They're all polys.
That they have different
They all
elements.
have multiple different atoms. Like, do they all have different elements, Gabe?
No.
No. They all have more than one atom. They all have more than one atom. Are they all positive or negative charged?
Yes.
That was a
Yes.
confusing way to say that. Yes, they are all either positive or negative.
They're all
Are they all either? I don't know.
They're all ions.
They're all ions.
All
And
have
my point is
charge.
they can be either positive or negative charge. They're not. Most of them are negative that we memorize, but there are more positive ones. But these combine in a similar way to these, except that these within itself, you should know this, within itself, BrO3, the Br and the 3 O's are covalently bonded. We'll get to covalent bonds in the next chapter. But these things are covalently bonded together, but all together they have a charge. So if we were to draw, instead of calcium sulfide, if we were to draw calcium peroxide, we would have these two oxygens that are covalently bonded, which as a group have a 2- charge. Two oxygens covalently bonded have a 2- charge, combined with our calcium 2+, and they're held together by,
It looks like Baymax.
I don't know.
You ever watch Baymax with the
Big
Asher?
grosses.
So let's say some properties of ionic compounds. Let's say some properties of ionic compounds. I'm going to erase the calcium thing. I'm going to erase this. I don't think you need to have a list of polyatomic ions in your notes because you probably, I hope, already have some. I'm going to erase the octet rule. Let's talk about the properties of ionic bonds real briefly, and then we'll talk about metallic bonds real briefly, and then we'll talk about naming. Because naming is the main thing you're going to be doing for this chapter. And it should be review. It should be review for your name, but I know that sometimes people struggle because we got very little time. Properties of ionic compounds. Give me some. You should have found some in your lab. Give me the ones from your lab, in fact, right now.
More ions per unit volume.
I don't know. I don't think that's a property of ionic compounds in general. You might have some.
Calcium bromate.
Okay, that's an example of one. Let me help you on your way a little bit.
How
So
does it smell?
usually these things are solid. Usually the compounds themselves are solid at room temperature. Usually, usually they are brittle and crystalline, meaning they form a repeating lattice. What's a lattice?
It's
crystal, a 3D crystal shape.
a normal lattice is a thing in building that I believe is very tacky, but other people like.
Good job, Gabe. So this, Gabe,
And it's
the
just-
tacky thing Gabe is talking about, I love that, Gabe. The tacky thing Gabe is talking about is that some people's like front porches have this like woodwork under here that's called lattice work. It's like a basket weave of wood. And Gabe, as like I and probably Lily, find it tacky. But it's a repeating pattern, almost like a chain link fence would count as a kind of lattice. So it has this repeating pattern, which we call a crystal lattice. The energy it takes to break that lattice for a mole of it is called, it's, what, you had this as one of your vocab words.
It's the. It's no, it's not personal lattice. It's
Lattice energy.
Yeah, lattice energy. I'm kind of led up to that like it was going to be some revelation, but it is just lattice energy. So they're solid, brittle, crystalline, and this is important, and this is, please pay attention. And this is part of Kessel and his lab. What did you find that the ionic compounds in your lab did?
They lit up the probe.
Yeah, they conducted electricity.
Conductive.
Conduct electricity, but only did the salt itself, when you just had salt, did that conduct electricity?
No.
No, it had to be dissolved in
Water.
water.
Because
In,
water is
so say
conductive.
this, in aqueous solution. No, the water wasn't. You showed that too, because you had pure
Yeah, that's
water.
what I said.
You had pure distilled water. Did that conduct electricity?
Yeah.
No. Distilled water? Taylor, did the distilled water conduct
Yes.
electricity?
Yes.
Try it again.
No.
The distilled water.
No.
No. Look at your actual table and tell me the truth.
No.
Did the distilled water conduct electricity?
No.
No. Distilled water did not conduct electricity. So pure water doesn't. Did pure salt conduct electricity? No. It has to be salt in aqueous solution. And when I say salt, I don't just mean table salt. The general term for ionically bonded compounds is salts. So if we were talking about, for instance, iron salts, those are all of the compounds that are iron chloride, iron sulfate, iron sulfide. Iron combined with any anion would be an iron salt, because salt is the general term that we use for an ionic compound. So these conduct electricity in aqueous solutions, another property of ionic compounds. And the fact that they're brittle is really important, because in our lattice, we have a repeating pattern, let's say of calcium and sulfide. Calcium, sulfur. Calcium, sulfur. So you have to repeat. You know this from the time you were in, what, kindergarten?
Science.
From the time you were in 8th grade science, you know this is called a pattern. It repeats. Right? What's the charge in the calcium?
+2.
This one has a +2 charge, the sulfur?
-2.
-2. 2 plus, 2 minus, 2 plus, 2 minus, etc., etc. If I hit this with a hammer, this is in your book, if I hit this with a hammer and these all move down 1, now we have sulfur touching sulfur and calcium touching calcium. Now what's going to happen between these two?
That's naughty.
They're going to do what?
Bond.
No, calcium and calcium? They both have a positive charge, so they will.
It retracts.
They're going to repel. This is the word you're looking for. They're going to repel. So that causes a break here and it shatters. That's what makes it brittle.
That's so sad.
Whereas, and this will be a nice segue into our metals, if we have metals, which bond as a sea of electrons, I hope you remember from physical science, metals which bond as a sea of electrons, it's all these iron, for instance, it doesn't have to be iron, but any metal, nuclei, kind of in a repeating pattern, or yes, in a repeating pattern, but instead of having them connected by the electromagnetic force, they're bound together by all these sea of electrons. Sea of electrons. This is in a metallic bond. Sorry, I should have made that clear. This is a metallic bond now we're talking about, not ionic. So the sea of electrons, if we do the same thing and we hit it with a hammer, the ions again all shift down 1, we'll say, but they're still bound together, just like they were before, but now they have a dent in them. So if you hit an ionic compound with a hammer, like salt, what happens?
It explodes.
It breaks, it explodes. If you hit a metal with a hammer, like iron,
It dents.
it dents, it's malleable. That's one of the properties of metals. So let's go on from there to properties of metals. One of them we just said is that metals are
Malleable.
Malleable.
Metals are malleable. What else? Ductile.
Solid.
They are. Most of them are solid.
Solid at room temperature.
Are they all?
No.
Nope. Mercury's not.
Have a high melting point.
Usually a high melting point. What else?
High density.
Usually a high density. There are exceptions. Lithium.
Yes.
What else?
Luminous.
You know what metals look like, right? They are generally
Shiny.
shiny. And they're shiny because of this tends to form a nice flat surface, and when light comes in, it bounces right back out, so they're reflected. So those are the properties of metals. Today we talked about properties of metals, properties of ionically bonded compounds, how ionic bonds form, and what it is to form a bond at all. We also made several allusions to advanced refrigeration. The objective, which I should have done at the beginning, come to find out. Oops. Tell me what the objective was.
Oh, it was-
Model the formation of ionic bonds.
Model the formation of getting a new marker of ionic bonds. Questions? What we didn't have time for today is to talk about naming ionic compounds. There are videos on my channel that you can watch about that. There are also good videos you can watch about that, and we will talk about it in class, and we'll do a worksheet over it. We will not probably do another video about it, but we will do a worksheet over it, and we'll talk about it in class. Questions? Because it should be review.
Nose. Aren't some metals also conductive?
We should have put the metals are conductive on here also, yes. Conductors of what?
Electricity.
Both heat and, ditto, electricity.
What does ditto mean?
Great question,
Same.
Taylor. Bye!